we are going to see a microwave filter. Filter is a two-port network. It has to control the frequency response at a certain point. That means it has to pass some frequency and stop or attenuate other frequencies. That is the nature of the filter. The filters are mostly used in communication network. It may be radar, wireless network, etc. An ideal filter, that is a ideal one. So its insertion loss is 0 and attenuation is infinite, and it has linear phase response in the passband. Passband means it has to allow the frequency, certain band of frequencies. So its insertion loss should be 0. Infinite attenuation means that is it has to block certain band of frequencies. That's why this is called stop band. Linear phase, that is phase variation is in a linear manner in the passband. So these are all the characteristics of an ideal filter, but practically this is not possible. So we go for practically realizable filter types. We have maximally flat filter or Butterworth filter, equiripple filter or Chebyshev filter, linear phase filter, and elliptic filter. These are the commonly available filters. If we want to design a minimum insertion loss filter, we go for binomial approximation method. So that type of response is called binomial response. In the binomial response, we are going to consider a power loss ratio. That is, power loss ratio means the ratio between available power from the source to the power delivered to the load. Power delivered to the load is incorporated by reflection coefficient. So this power loss ratio is used to calculate the insertion loss of a network. Now, the maximally flat filter means it has flattest possible passband response. So, to design a maximally flat filter, PLR ratio is, or power loss ratio is 1 plus k square into omega by omega c to the power of 2n, where n is the order of the filter, omega is the frequency, instantaneous frequency, omega c is the cutoff frequency. 1 plus k square is used to design or it is used to fix the ripple, passband ripple of the filter. Here we have a curve, characteristic curve of a filter, that is maximally filter and equiripple filter curves are here. Now we are going to see the maximally filter or Butterworth filter. At cutoff frequency, that is omega by omega c equal to 1 point, we are getting 1 plus k square. That is the maximum ripple or band edge ripple. Now, within the passband and away from the passband, the characteristic curve is more or less in a flat manner, or The curve is monotonically increasing within the passband and are also in the stop band. That is the characteristics of a maximally flat filter. Now we are going to design a filter. That is, the first one is the order of the filter. Order of the filter means how many components are used to construct a filter circuit. That is calculated from the following equation. That is, LA of omega dash equal to 10 log 1 plus E into omega dash by omega 1 dash to the power of 2n to the base 10. It is in dB, where E equal to antilog of LAR divided by 10 minus 1, where LAR equal to band edge power loss ratio. For a maximally flat filter, its value equal to 3 dB. So from this, we are getting the unknown parameter n, because omega dash is the attenuation frequency. This is in a stop band frequency. So how much attenuation is required in the stop band? That is used here. So, for example, minus 15 dB is required at 4 gigahertz. So, omega dash equal to 2 pi into 4 into 10 power 9 and LA equal to 15 dB. So, the only one unknown parameter is n. That is calculated using this formula. If we get the order of the filter, we are going to draw the prototype filter structure. Why it is called a prototype filter structure? Because the low pass filter is constructed using a normalized element values, that is normalized with respect to impedance and frequency. So the source and load impedances are equal to 1 because it is normalized with respect to the impedance. The other elements, the inductor and capacitor values, are normalized with respect to impedance and frequency. Here we are having two types of structures. One is capacitor, inductor, capacitor, inductor. Another one is inductor, capacitor, inductor, capacitor. These two circuits are used to realize a low pass filter. These two circuits give the same response because this is a dual structure. Here GK is the inductor in a series element or a capacitor in the shunt element. These G values are calculated using a single formula or simple formula, that is Gk equal to 2 into sine of 2k minus 1 into pi divided by 2n. K varies from 1 to n. N is a fixed one. So K varies from 1 to n. We are getting several sine of pi values. So from this we are getting the normalized filter element values. Then we are going to implement the impedance and frequency scaling method. So if we implement the scaling, we are getting the original L and C values of the filter structure. For a low pass filter, Lk equal to R0 Gk by omega C. R0 is the characteristic impedance, omega C is the cutoff frequency. Similarly, we are having Ck equation. Ck equal to Gk divided by R0 omega C. Now, we are implementing these equations. We are getting the capacitor and inductor values for a particular frequency and the given or a required impedance value. For an example, design a maximally flat low-pass filter with a cutoff frequency of 2 GHz, impedance of 50 ohm, and at least 15 dB insertion loss at 3 GHz. So this is our given problem. For this given problem, the data are LA are equal to 3 dB because this is a maximally flat filter. That's why LAR is a fixed one, that is equal to 3 dB. Then LA, this is equal to 15 dB at 3 GHz. So that frequency is F dash. FC equal to 2 GHz. Now the unknown parameter is N. This N is calculated from the first two equations. If you are substituting these values into the first two equations, we are getting N equal to 5. That is approximately equal to 5. Then, using the G formula, that is GK is calculated from the above mentioned equation. From this, we are getting the GK values. These GK values are implemented in the prototype structure. Then we are introducing the LK-CK equations, that is denormalize the normalized parameter with respect to 2 GHz and 50 ohm. We are getting the original L and C values. That's why we are having a picofarad and nanohenry values, unit values. Now the circuit is capacitor, inductor, that is minimum number of inductances are used in the circuit. This circuit is realized in the ADS structure, ADS software. That is, this is the structure. At the input and output side, we are using termination impedances. Then this circuit is simulated and we are getting the S parameters. That is, S11 means return loss of a circuit. S12 or S21 means transmission loss or insertion loss of the circuit. Here, the given data is the filter has to pass up to 2 GHz and 15 dB is required at 3 GHz. So these are all the specifications of a filter design. Now we are putting a marker on the graph. That is, we are having 3 dB at 2 GHz, that is the band edge frequency. Then 17 dB at 3 GHz, that is more than 15 dB. So we are satisfying the given specification. So the order 5 filter is designed, simulated using the ADS software. Thank you.